Good morning, ladies and gentlemen. Good morning, friends. I welcome you on the first contributed session of our ECSQARU conference. I want to invite all the audience which are not only here but in all of the world joined either online, or I can also invite people who will listen our session or other sessions streamed later in the evening or other day. So we are now in the place where Billy Function Conference took place 5 years ago, and we are starting the Billy Function session. The other one will be on Thursday afternoon. I'm on the wrong place. So let me introduce first speaker. This contribution is joint work of 3 authors. Games, the title is Games of Incomplete Information, a framework based on Billy functions. And it will be, come here please, it will be presented by the third author, Pierre Pomeray. So, it's your time. You have 15 minutes for your presentation.
Okay, thank you very much. Thank you very much. So, I am Pierre Pomeray, and I will present the work we made with my PhD supervisors, Hélène Fargier and Eric Martin-Dorel, at the IRIT laboratory in Toulouse, France. So the title is Game of Incomplete Information, a framework based on belief function, and it's a work which belongs to game theory, the study of multi-agent decision making. So let's start with a basic example of game of complete information.
Sorry, we are not sharing.
We are not sharing it, sorry.
Are we?
Oh yeah, we are. Okay, so sorry. So in this example we have 2 agents, agent 1 and agent 2, which are criminals, and they both are looking for a partner to perform some mischief. So they can choose either Quentin or Rose as a partner. If they choose the same partner, they will earn $2,000 each, and if they choose different partners, they will earn $3,000. So one can define this game using the mathematical normal form with a set of agents, a set of action per agent, and a utility function per agent. But in the 2-player finite case, it is quite more readable to define it with a utility matrix. Then the complex example, which is a game of incomplete information, is inspired by the Peter, Paul and Mary example. So our 2 potential partners, Quentin and Rose, are suspected of the murder of Mr. Jones. In fact, there are 3 suspects, Peter, Quentin and Rose, and Big Boss, who ordered the crimes, flipped a coin to decide if the murderer will be a man or a woman. It is not a fair coin, so there are 60% chances that the murderer is a man and only 40% chances that the murderer is a woman. Our 2 agents, they will still want to choose a partner. They cannot choose Peter, they only can choose Quentin or Rose. If an agent chooses the murderer, she will not earn anything. On the contrary, if she chooses someone who is not the murderer, she will earn $2,000 or $3,000 as previously. Furthermore, each agent has some private information. Agent 1 will investigate on Peter, so she will know whether Peter is the murderer or not. And similarly, agent 2 will know whether Rose is the murderer or not before she chooses her partner. So we can express this situation with the possible underlying worlds. There are 3 possible worlds. There is omega p, the world where Peter is the murderer. In this case, agent 1 will learn that Peter is the murderer, of course, and agent 2 will learn that Rose is not the murderer. And in this case, they will play this kind of complete game which is identical to the previous example. In the second world, omega q, Quentin is the murderer, so we also know what will learn the agents, and we also know which game they play in this case. It is another game with some zero payoff in case of someone choose Quentin. In the third world, Rose is the murderer, and as we also know what will learn the agents and what game they will play in this case. So this can be expressed in terms of underlying worlds, but this can also be expressed in terms of private information, the private information agents receive, and that's the approach we will use in this presentation. So formally, a Creedle game, it's defined with such a tuple, where n is the set of agents, and so we have two agents, agent 1 and agent 2, and for each agent we have a set of actions that is her possible choices. So both agents may choose either Quentin or Rose as a partner, and for each agent we also have a set of so-called types which correspond to the private information they have. So agent 1 will learn whether Peter is the murderer or not, and agent 2 will learn whether Rose is the murderer or not. Finally, for each agent we have a utility function which corresponds to the three previous complete games, depending on the type configuration, because of the utility function depends both on the action chosen by all agents and on the private information they receive. And at last we have a mass function which encodes for a belief function, and that is the prior knowledge of our problem. So we have two focal elements. We have a first focal element which corresponds to the set of possible type configurations that may occur when a man is the murderer, with a weight of 60%, and one other focal element which is the only type configuration which may occur when a woman is the murderer, with the weight 40%. So this can also be drawn as a matrix of matrices, and we find back the three possible complete game depending whether who is the murderer, and one fourth complete game which is impossible because it corresponds to an impossible type configuration. So to study such Creedle game, we need a few concepts, and the first concept we need is the concept of strategy. A strategy of a given agent tells what the agents will choose depending on the private information she had learned. So it is simply such a function from the set of a type to the set of her actions. For example, a strategy for agent 1 may be sigma star 1, which tells that if agent 1 learns that Peter is the murderer, then she will choose Quentin as a partner, and if she learns that Peter is not the murderer, then she will choose Rose as a partner. Similarly, a strategy for agent 2 may be sigma star 2, which tells that if Rose is the murderer, agent 2 chooses Quentin, and if not, she chooses Rose as a partner. A strategy profile is a strategy for each agent, so it's simply a vector of such a strategy, like it is sigma star. Then we have the question of what utility do we consider for a given strategy profile, and we have two questions to answer. In fact, we have the question of the knowledge revision, because each agent will learn some information, and we have the question of how to generalize the expectation. So for the knowledge revision, we use the Damsel rule of conditioning, which is adapted to this, which fits this example, sorry. So recall that a mass function can be described, belief function can be described by a mass function, which assigns the masses or the chances to possible set of the world, of set of type configuration in our case. So the prior knowledge is as it. We have 60% chances for the two type configuration corresponding to the man is a murderer, and another focal element with a mass of the 40% for the woman to be a murderer. So when revising knowledge using the Damsel rule of combination, consider for example agent 1, when he learns that Peter is not guilty, is not the murderer, so he will focus on the remaining the type configurations that remain possible, the white area here, and the mass that were assigned to this big set is transferred on the subset that remain possible, so this type configuration. And then, to generalize the expected utility, one of the classical approaches is to use the Choquet integral or Choquet expected utility, which can be expressed as a summation using the mass function. So we use the mass function with the revised knowledge because we have interest of of the behavior of agent I, given that the information theta I she had learned. And as example, we can see as those two Choquet expectation computed for the strategy profile sigma star. In the first case, we look at agent 1 when she learns that Peter is not the murderer. So as we see, it focuses on the two type configurations that remain possible. So here he has probabilistic knowledge after this revision. So he computes one classical expectations. On the contrary, if we have interest of agent 2, when she learns that Rose is not the murderer, she revises her knowledge and focuses on the white array. So she is in complete ignorance between those two type configuration and will consider her worst case. So we have all we need to define the usual concept, and one of the most treated concepts in game theory is the Nash Equilibria, which are strategy profiles such as no one has incentive to change a strategy, whatever the type. So the strategy profile sigma star, the same as before, is a Nash Equilibrium. We can check that in the four case there is no better choice than choosing the assigned action, but it's not very interesting. What is interesting is to note that if we use a classical Bayesian game, a probabilistic Bayesian game, to model this situation, sigma star will not have been a Nash Equilibrium, and on the contrary, sigma b, which differs here, would have been a Nash equilibrium. It is because of the well-known knowledge revision with the probabilistic approach, which is not suited for this kind of knowledge. If we use a probability, we have to dispatch the chances among the possible type configuration. So consider agent 1 who learns that Peter is not the murderer. The probability that were assigned to this type configuration is not transferred, it is discarded. So it happens that Rose becomes more likely to be the murderer than Quentin. And it is not the case using the belief function theory. And that's why using a Bayesian game, agent 1, if she learns that Peter is not the murderer, she rather choose Quentin, who is less likely to be the murderer. On the contrary, using a Creedle game, she rather choose Rose. Last, we checked that there exists some kind of Selton model for Creedle games. The idea of the Selton model is to consider that the pieces of private information are some kind of agents. They will choose their own action and they will earn their own payoffs. So it is sometimes known as Olson and Rosenthal theorem, since they implement the transform that yield the Selton model in the two-player Bayesian case. Their transform yield a polymatrix game, which is a game of complete information, and it is succinctly represented as a graph of two-player local games. So we generalize this transform to any number of agents, and of course to a belief function. So our transform yield a hypergraphical game, which are also game of complete information. In fact, they generalize the polymatrices, allowing to have local games with more than two players. So it is very important because they are game of complete information, and so they belong to the classical game theory. And so we benefit both the theoretical results and the algorithmics for classical game theory and hypergraphical game also. So an hypergraphical game, as I said, is a game of complete information. It's just a standard game, but it is given as an hypergraph of local game. So we have a set of agents which form the vertices of the graph. We denote them with circles. And we have some local games. We are the hyperedges of the graph, and we materialize them with boxes. There are local utility functions defined for each local game. And when an agent chooses her action, he will play it in every local game she is involved in. and so her global utility will be simply the sum of her local utilities. So now I can present the transform. How do we cast our example Creedle game into a complete game, an hypergraphical complete game? Step by step, we will first build the vertices. There is one vertex for each possible type, so we have 4 vertices here on the right. And then we will build the local games, one local game for each focal element, that is, element which have a non-zero mass. So recall that a vertex denotes for a type, and focal elements denote for a set of type configuration. So a given vertex play in a local game if the type is possible in the corresponding focal element. Then about the local utility functions, we define them so they correspond to the part of the Choquet expectation which concerns this focal element B, and we show that this formula correspond to an on-the-fly Damsel conditioning. And that's why we can conclude that the global utility of a given vertex I theta I will be equal to the Choquet expectation of agent I if she have learned that theta I for every agent, every possible type, and every strategy profile. And so as a corollary, we have the fact that both games have the same Nash Equilibria. Last, we check the complexity of the transform, which is in the size of the original Creedle game at the power k, or k plus 1, where k is the cardinality of the biggest focal element. So if k is equal to 1, we will find back the probability case and the Rosenthal transform. And if k is small, we hope this transform to be tractable if the game is also reasonable. So to conclude, we define Creedle games, which are incomplete games generating the classical Bayesian game. And we also prove 2 Austin and Rosenthal-like transform. We link Creedle games to the classical game theory. As further work, we aim to generalize a bit further this model, allowing to use other kind of capacities, and also to study other decision approaches and knowledge revision approaches, both for belief function or for general capacities. One of the thoughts is that we have an ongoing formalization using the core proof assistant, which is a piece of software which can check that proofs are correct, and so we are expressing this result in our proof library. Thank you for your attention.
Are there any questions or comments from the audience here? So we have to ask people from audience online. Have you any questions or comments, please? Nothing in check. Okay. So thank you again, and it's. And now it's turn for the second speaker. It's a joint work of Radim Jiroušek with Václav Kratochvíl, approximation of belief functions using compositional models. And you can see both the authors here now, but it will be presented by Radim Jiroušek.
Thank you, Vašek, for helping me with presentation. I want to say also hi to all online participants, among which there are a lot of my own friends, and I am sorry not to meet them face to face. So hi, everybody. Okay, I am speaking. I am presenting a topic which is caused by Vašek, but I should say that it belongs to the topic we have been solving with Prakash Shenoy for in a long time cooperation, so naturally what I am speaking about is also influenced by him. I want also to say that this lecture is exactly among those in which authors take an interesting issue from probability theory and study whether this can be extended also to belief function. So we are now speaking about an approximation which was introduced by Albert Perez in the 70s and which he called approximation of probability distributions by simplifying dependent structure. So let us start considering multidimensional probability distribution and take the whole bulk of these variables and make a partition. Assume that the elements of this partition are rather small set of variables. And having this, everybody knows that using a so-called chain rule, one can express this multidimensional distribution as a product of marginal conditional probability distributions. Have a look at the last term of this product, which is a conditional probability distribution of a small group of variables, here denoted by U sub n, and conditioned by all the remaining bulk of variables. So it is very probable that this small group of variables can be well described when knowing a much smaller group of variables, not all the others. So therefore we can find a small subset of the whole remaining group of variables such that these two conditional probability distribution would be practically the same. And we can substitute this smaller conditional probability into the chain rule presented above. So we can do this also with other conditional distributions, and having now a product of conditional probability distribution of this form, which is here denoted by kappa. So this product is called an approximation, or if you want to use this Perez term, it is a dependent structure simplification approximation of a probability distribution. So this is a probabilistic idea, but first, before we start speaking about belief functions, we have to say how to recognize whether the approximation is good or not. So for this we can use, in probability theory, very often use Kalber divergence, and thanks to the fact that Shannon entropy is additive in the sense of this equality, we can express this Kalber divergence in this form. So what is important to notice that this can be expressed as a sum of two terms, and the first is a negatively taken entropy of the original distribution, which is being approximated, and the second term, which can be completely computed from the approximation, from the distribution kappa. So in a special case, in some special case, it is just its entropy. But in general case, it can be expressed as a sum of these conditional entropies, or this sum of these differences presented here. So what is important to notice is the fact that minimizing Kalber divergence minimizing these expressions, which are completely, can be completely computed from the approximation. So therefore, we can optimize the approximation even if we don't know the original probability distribution. So it is just based on the assumption that the distribution from which the approximation is constructed, so that it is marginal of the that these are marginal of the original distribution. So this is a probabilistic case. Now let us consider very functional. Let us consider basic assignment, and it's quite interesting to mention that the basic assignment is in general case given by a number of parameters which super exponential grows with the number of variables. So it stresses the importance of any approximations because you can't work with multidimensional constructions which needs such a great number of parameters. So, okay, when we consider small dimensional basic assignment, we need some way how to construct from this more dimensional one. In probability theory, it was just this multiplication of conditionals. Here, you who know me can expect that I will use for it a composition. And the composition is a binary operator. Composition is a binary operator for Billy functions meeting these four axioms. In fact, we know that there are two types of composition, or at least two types of composition defined for Billy functions, but we needn't care about which one is used because what I'm speaking about holds for both of these composition. In fact, it holds just for any operator meeting these four axioms. So it means that having small dimensional marginals of some basic assignment, we can consider approximation of this form. So we assume that M sum I is a small dimensional basic assignment, and from this is, we can get a multidimensional one. Knowing that generally this operator is not associative, we have to take care in which order it is used. And from the axioms, we can deduce quite simply that M sub 1 is a margin of this approximation of this multidimensional model. In fact, any prefix of this model is always marginal, but it means that M sub 1 connected with M sub 2 is also marginal, but it doesn't mean that M sub 2 is marginal. So neither M sub 3 need to be marginal of the resulting approximation. If this happens, so it is nice, and then we call the model perfect. Model is perfect if all the building blocks from the model are marginals of the resulting model. It means that the model expresses or keeps all the information which is contained in this in the given margins. So we start solving the problem. Then we have a marginal basic assignments of some multidimensional one, and we want to construct an approximation from this given set of marginals. And the question is how to detect the permutation in which the marginal basic assignments, small dimensional basic assignments are connected to get the best approximation, or another question, whether any entropy which is known for B function can be used as a criterion for detecting the optimal approximation. So what we know? First, we know that there are at least 30 of different functions, entropy-like functions. Some of them are called a measure of conflict, and different other names are used, but at least 30 of them there are, but only one of them is subadditive, additive in the sense we showed for Shannon entropy. So therefore, this entropy gives some type of a chance that it could be used because of this property as a criterion to recognize the best approximation. Then what we also know is that if we have a perfect model, perfect approximation, then it is the optimum one. I already mentioned it is because it contains all the information which can be got from this marginal. And the last piece of knowledge we want to utilize is that if we have a permutation of marginals in the way that the sets of the variables meet the running intersection property, then there exists permutation giving the perfect approximation. And this is, we started, and based on this knowledge, we started realize some experiments, computational experiments. We took 26-dimensional, we started to consider 26 variables, and for them we randomly generated 110 basic assignments. In fact, we didn't generate this multidimensional basic assignment, but just the marginals, which from which we constructed the distribution. Then we, for each of these situations, we generated 20 permutations, and one of them, exactly one of them was perfect. So one of them met the running intersection property, so therefore we knew which model was the optimum one, and therefore having a criterion function, we could check whether how behaves the difference between the non-optimum approximations and the optimum by this difference. So we started to check this Shannon's entropy, which is additive, and we got something like this from this plot. We can see that about half of them approximation has a value lower than the optimum, another half higher than the optimum. So therefore, we couldn't use this entropy as a criterion to detect the optimum one. So therefore, we introduced a heuristic function which is based on some other entropy, but this entropy can't be computed for a multidimensional model, so we deduce from it just a heuristic function which can be computed for any model, compositional model, and for this we got rather unexpected results, because from this we can see that using this heuristic function, we could detect all optimum all optimum approximations as optimum, and only 3 times it happened that we found also a non-optimal approximation which had the value same as the optimum one. So therefore we can somehow recommend this heuristic function as a criterion function for detecting the quality of approximation. That's all what I wanted to say. Thank you.
Thank you for your presentation. I want to ask if there are any questions or comments from the audience. It's a little bit complicated here behind the monitor. I cannot see you. So Milan, ask please.
Okay, so you have mentioned in one of your last slides some decomposable entropy for these functions in your paper with 2020 with Prakash. So my question is whether this only decomposable entropy corresponds to some conditional independence concept.
Yes, exactly. It is. It corresponds. Then, if you then it is a question what type of conditional independence entropy were in mind. So it really corresponds with the independence defined by Damsel rule of Damsel's combination.
Yeah, thank you.
I was interested in the definition of composition. It kind of reminded me a bit of belief revision kind of axioms. Do you know whether there's any connection in that direction?
Well, if I do understand your question, I am afraid you are asking for something what should be done in further time, because you are asking for what we could do with the approximation. Now I am only speaking about how to get an approximation.
It's just an issue in terms of your definition of your axioms for compositions reminded me a bit of the axioms for belief revision. I just wondered whether there was a connection. But
I don't think this type of general composition doesn't have anything in common with belief revision, because it guarantees only that we can get a more dimensional belief function from low dimensional. And for example, one of the defined composition just speaks about factorization. So it doesn't have a semantic of belief revision. This one composition operator has a semantic of factorization, that it simplifies, formally simplifies how to get multidimensional one.
I've another, if no one else has a question, I've another quick question. Is it possible to compare it with other approximations? Are there alternative approximations, and if so, does it do better than those?
So I must say that I don't know the approximation you are speaking about. So
I suppose there have been other approximations in the literature, for example, based on sampling or Monte Carlo algorithms of various kinds.
I can't answer your question.
Okay,
I don't know.
No problem.
Okay, thank you for your questions, and we now to have asked people from online audience. Can you hear me, please, Luis Godo or Davide Petruti? Can you hear me? Or I have so.
Yes. Can you hear me?
Okay, we can hear you. Have you, some of you or the other online attendee, some questions to Radim? It looks like not. So let me thank to Radim again.
Thank you.
And let me introduce the third speaker, because our conference is hybrid. So the third speaker is not here in Prague. He is in Italy. Davide, are you in Perugia?
Yes.
So third speaker is Davide Peturiti. He is in Italy, Perugia, and the title of the speech is Damsel Approximation and Probabilistic Bounds in Statistical Matching. So Davide, it's your turn. You have 15 minutes now.
So thank you so much. Can you hear my presentation and can you see my presentation?
Yes,
Okay.
yes, we can see and we can
Thank you
hear.
for the organizers and for the opportunity of participating to this conference. This is a joint work with Taggi from La Sapienza University of Rome. I will start my presentation with some preliminaries in order to fix the notation and the terminology. I will refer to a finite Boolean algebra of events and to a real function defined on it and ranging in a unit interval, which is grounded and normalized. It will be called a probability measure if it is additive, as usual, a belief function if it is completely monotone, a true monotone capacity if it satisfies the monotonicity property just for pairs, and a coherent lower probability if it is the lower envelope of some closed set of additive probabilities. Normally, for the set of probabilities generating a lower probability, we take the largest one, which is the core, or also said the cradle set in the imprecise probability community. Okay. As is well known, probability measures are particular belief functions, which are particular true monotone capacities, which are particular lower probabilities. We will focus on the class of belief functions, which have been characterized by Damsel and Schaeffer. As is well known, belief functions are completely characterized by their Mobius inverse, which is the so-called basic probability assignment, which is a non-negative function defined on the algebra, grounded and summing up to 1, that allows to recover a belief function through summation. And every belief function is connected to a dual function set plausibility function. Continuing with the preliminary, I'm close to the end of the preliminaries, by the way. We refer to the notion of conditional probability due to Dubins as a two-place function defined on a product of an algebra with the set of non-impossible events of the algebra asked to satisfy the three conditions reported in the definition. I won't enter into detail. Nevertheless, the fact that the algebraic structure of the domain plays a crucial role in the definition. So if we want to remove the hypothesis on the domain, we need to introduce coherent conditional probability as a function defined on an arbitrary non-empty set of conditional events that can be extended to a full conditional probability on the corresponding algebra A. This is a particular case of a more general notion of coherent lower conditional probability in the sense of Williams, which is a function, a real function, that is the restriction of the lower envelope of some closed set of full conditional probabilities. So I'm done with the preliminaries. I can start speaking of the main topic of the presentation, which is the statistical matching problem. In the most simple case, statistical matching amounts to having two sources of data, A and B. We have X that denote common variables to both sources, Y are variables collected only in the first source, and Z are variables collected only in B. So from construction, we have data divided in two samples, one on the variables X and Y, and the other on the variables X and Z. So from data, we can estimate the probability distributions of Y given X from A, Z given X from B, and the and the marginal probability on X from both sources. Under suitable assumptions, we can estimate this probability distribution with maximum likelihood, essentially through observed frequencies. So far, so good. So this is the input of statistical matching problem. Now I'm going to formulate the problem from a probabilistic point of view. So we have 3 random variables, x, y, and z, that are categorical random variables with finite range. Possibly they can be also multidimensional. Every random variable determines a Boolean algebra of events spanned by the partition induced by the corresponding range. We also have a vector whose components are x, y, and z. And here we assume, and this is an important assumption, that the 3 random variables are logically independent. So there are no logical relation in between the 3 random variables. This means that the vector is connected to a Boolean algebra, which is just the Boolean product of the 3 independent Boolean algebras. So given a measure on the Boolean algebra of V, it induces a probability distribution for the vector in the usual push forward way. Okay, so we have this assessment that comes from statistical matching. I have a probability distribution of Y given X, Z given X, and the marginal on X. So the statistical matching problem amounts in finding a joint probability for the vector. And this can be translated essentially in a problem of coherence of the above assessment. Vantages proved in 2008 that under the logical independence assumption of the 3 random variables, essentially the assessment is coherent. So this means that we can always find a joint probability for the vector, which in general is not unique. But even more, we can find also a full conditional probability consistent with the assessment in pink. Of course, also the full conditional probability is generally not unique. Concerning the joint probability of the vector, we have in general a closed and convex set of probability distributions inducing a lower and an upper envelope, which are lower and upper probabilities. But even more, if for every fixed small x, we consider the sub-assessment composed by the 2 conditional distribution y given x and z given x for the fixed value of x, it will induce another closed convex set of probability for y and z, given that x takes the small value of x that we have fixed. Of course, also this set of probability will induce a lower and an upper probabilities. Okay. The lower joint probability of the vector has been characterized by these UN vantaggi. The lower probability of the other set of probabilities, those for y and z, given that x takes the value small x, can be easily characterized through Fréchet-Hofding inequality, as reported in the slide. It turns out, and it's immediate to see that none of these 2 lower probabilities are in general too monotone. So our idea in this presentation, in this work, is to approximate for every chosen value of x the lower probability in orange of y and z, given that x takes the value small x, with a belief function. Why is it important? Because if we have such an approximation, we can define the conditional belief and plausibility function in red of y and z given x for varying small x, so varying the value of the variable x as a conditioning. In turn, if we have the belief and plausibility functions in red, we can define a joint belief and plausibility function for the vector. Okay, so a joint belief and plausibility function, essentially taking a mixture of the 2 functions in red with respect to the marginal probability distribution, okay, the original in the assessment. So we have proved that the 2 joint belief and plausibility functions built in this way are actually dual, and they extend the marginal probability on x. So they are locally a probability on the algebra of the variable x. Further, they allow to recover the conditional belief and plausibility function of y and z given x and the corresponding plausibility through ratios, okay, provided that the marginal on x is positive. We do not postulate that the marginal is everywhere positive. So in general, the joint belief and plausibility in blue do not allow to recover all the conditional function in red. So we need to keep trace of them. So the functions in red, in particular the belief function of y and z given x, is actually a collection of belief function on the algebra of y and z. given each possible value of x. So in principle, we could think to merge them, to combine them through the Damsel rule of combination, but it is not suitable, neither from a semantic point of view, and also because the final result will be a belief function on y and z, completely disregarding x. Okay, so our procedure actually gives a joint on all the vector. Okay, so we need to propose some strategies to arrive to such an approximation. The first idea is to have an inner approximation. What does it mean? That for every small value of x, we look for an inner approximation. So we look for a belief function that pointwise dominates the target lower probability. We have proved that every belief function that dominates the two conditional distribution of y given x and z given x, and this is a necessary condition for having an inner approximation, is actually additive, and even more, it is an element of the core of the lower. So computing an inner approximation is actually not really meaningful because it amounts just in choosing an element of the core. So another possibility is to compute the outer approximation. So we search for a belief function that it is pointwise dominated by the target probability. In doing so, we adopt the approach proposed by Miranda, Montes, and Bicig in a series of papers that amounts in looking for the belief function that outer approximates and is closest to the target lower probability according to a fixed distance. This essentially translates in solving this optimization problem where we minimize the distance between the target probability and a belief function that is an outer approximation. So we have different choices for the distance. The main three choices are those reported in the slide. The distance d1 essentially gives rise to a linear programming problem, but results in a non-unique optimal solution, which is always undominated. That means that we cannot find a different belief function which is pointwise comprised between the optimal solution and the target probability. Another possibility is to choose the second distance that gives rise, so D2, that gives rise to a quadratic programming problem. In this case, we have uniqueness and undomination of the solution, but the price to pay is a quadratic programming problem. Then we have another possibility is the distance D infinite that can be translated to a linear programming problem with an extra scalar variable. In this case, we lose both uniqueness and undomination. Of course, the approach of minimizing a distance is just one of the possibilities. For instance, we could also think to minimize a measure of non-specificity or imprecision as done by Deneuve in a different problem. We want to stress that the problem we are facing in computing an outer approximation is actually a computational R problem, since we have an exponential number of unknowns and inequalities in general. Okay, this is an example. We consider three random variables dichotomic and ranging in the set 0 and 1, and we consider the conditional assessment of y given x and z given x when x is equal to 0 in light blue. In this case, the target probability is the first row in the table, the one denoted with the orange lower probability. This lower probability is easily verified not to be too monotone. So we compute the outer approximation with the distance d1, and we discover that actually there are many possibilities, many optimal solutions. Two of them are the second and the third row in this table. It actually turns out that the last line, so the belief bell 2, is an outer approximation which is also optimal according to the other two distances, d2 and d infinite, and so it is also undominated. Okay, the last proposal that we consider is to approximate the target probability with an epsilon contamination model. So we fix an element in the core, and we fix an epsilon, which is a contamination parameter. And we consider the epsilon contamination class in the jargon of Huber. Was lower envelope is actually a belief function whose structure is reported in the slide. Well, this belief function can be used as an approximation, but what we get is that in general, it is never an inner approximation, but neither an outer approximation. Okay, why is it nice, this construction? Because independently of how we make the approximation, the final result is a joint belief function for the vector and a conditional belief function for y given z given x. The global assessment is actually a coherent lower conditional probability assessment in the sense of Williams, and this means that there is a closed class of full conditional probability on the algebra of the vector BV, whose lower envelope agrees with the given assessment. So we can compute the least committal coherent extension of our assessment to any possible new event in the algebra of the vector. This amounts to take as calligraphic Q, so as the set of all the full conditional probability agreeing with the assessment, the set of all dominating full conditional probabilities. It is easy to prove that in many cases, the least committal coherent extensions also said the natural extension of the assessment just boils down to compute a generalized Bayesian updating rule with the ratio reported in the slide, provided that the denominator is positive. Of course, we need to also take care of the case of a denominator which is 0 to have a complete characterization. But in any case, it is possible to provide a complete characterization for the general case. Okay, I finish with a toy example continued. I consider the conditional distribution that I took before, and I assume that the conditioning of 0 on 0 gives rise to the same conditional probability distribution that conditioning on 1. So we can take the outer approximation that we have computed before for both values of the variable x, and this gives rise to our belief function conditional on y and z given x. We fix the marginal on x to 1/2 and 1/2, and so with an easy computation we can compute the least committal extension on the event x equal 1 given that y and z are both 1. And this amounts to compute this ratio involving the joint belief and plausibility function on the vector. Okay, so it is quite nice. Okay, we have our procedure essentially amounts in approximating the target probability of y and z given x. Okay, and it's okay. I finished it. Okay, sorry. You can ask me if you want to question. Sorry.
Are there any questions from the audience? Yes, Radim Miroshek has question. Ask, please.
Davide, do you hear me?
Yes, not very well, but I can.
It's just a very short and simple question. Is there a difference between your assumption of no logical dependence and positivity of a distribution?
I think the positivity, okay, we assume that there are no structural zero from a statistical point of view. So essentially, from a logical point of view, it means that the algebra spanned by the vector coincides, is isomorphic actually to the power set of V. If you assume some logical relation, you have some atoms which are impossible, and so you lose the isomorphism with the power set of V. You are asking if the positivity of what? Sorry, Radim, can you repeat?
Well, you have this assumption on
I'm not assuming anything on the measure, okay? So that the probability distribution can be whatever, okay? I assume that the random variables essentially are logically independent partitions. So all the conjunctions are possible.
Okay, thank you. Is there any other question?
Okay, so Raphael, in the beginning, you mentioned the concept of coherent lower conditional probability by Williams, 1975, something like. My technical question is because I don't know whether this concept it's related to this coherence theory following this Italian school, whether it has something common with this coherent lower probability as dealt in context of imprecise probabilities by Wally and these people. Is there any relation?
Yeah, of course, if you work in the finite case, so you have a finite algebra, the theory of Wally actually coincides with that of Williams, essentially, because the difference is that Wally asks a property of conglomerability, okay, that is not asked by Williams, but in the finite case, it is automatically satisfied, essentially, okay? So it is very in this finite case is not that far from Wally theory. Okay, and it's actually connected also to the work by Giulianella Coletti and Scozzafava. Okay, it is just a different characterization of the same concept. Okay, they work with linear systems, sequences of systems. Okay, we work here from a functional point of view, but it's the same concept, can be characterized also in terms of systems. So, I don't know if I have answered, Milan.
Yes. Okay.
Now there is a question.
Okay, so next is question by Enrique Miranda. Enrique, it's your turn.
Okay, hi.
Hi, Erika.
Oh, Davide, thanks for the talk. Yeah, so it was, well, and hi everyone. Yeah, it was a question and a comment. The question is, when you have this unique or this approximation with the belief functions that you mentioned at the end, I guess you could extend it to the case of two monotonicity because you have a formula like a regular extension, or actually this only works for belief functions?
Let me check. Okay, the problem, I think it's the same because what makes the difference is how to build the joint, because you take the mixture of conditional beliefs is a belief, so you have preservation. If it would be a conditional two monotone, it would be a joint two monotone and two alternating. So I think that in principle you can extend the result also to, and essentially you would use your result for the two monotone case in computing the outer approximation. So I think that in principle you can generalize to that case. You are not very tied to work with beliefs.
Okay, also because for what you were saying about the approximation with epsilon contamination, even if it is not an outer approximation, but if you consider an outer approximation with epsilon contamination models, in that case, there is a unique solution, because this was, I think, in one of the papers with Ignacio and with Paolo.
Yeah, but the problem here is that you outer approximating a particular lower, no? Which is the lower of the set in orange, okay? And you discover that the belief you get cannot be an inner approximation because otherwise would be a probability, okay? So the only point is, can it be an outer approximation? In general, you have that it can be, if you take an element in the interior is positive. So if epsilon is positive, the lower is everywhere positive, okay? But the belief, sorry, but the lower is zero somewhere. So it cannot be an outer approximation.
Okay, I see.
So there are a problem on zeros.
Yeah, and this was also the same for us. So
yes, I guess, because we started from your work.
Okay, thanks.
Okay, so it's time only for last short question.
There is a chat question from Jürgen Landes.
I think it's a comment.
It's just the comment, it's not the question.
Okay, thank you.
Thanks.
Do you want to read out your comment, Jürgen?
Okay, so
Jürgen, do you want to read it out?
Sure, if you want to. So the problem of statistical matching and this kind of things of extending probability functions, which are only defined on subdomains, is also considered in standard probability theory. So not belief functions, but standard probability theory. And I'm just giving some links for people who might be interested in that. That's all.
Okay.
Thanks.
okay, so thanks to David for his presentation. Thank to all of people who have asked, either from here or from online audience. Jürgen, you have something else to add? No. So now it's time for 10 minutes short break. So we will start at 11:55 and there will be another session